Swayam Prabha. Digital India. Educated India.
So we take the discrete structure and we show all the analysis and solution procedures, which are essentially same as the FEM procedures. The advantage of these discrete structures is the identification of the elements, identification of the nodes, and identification of the parameters and solution. They are much simpler. To start with, yesterday we were talking about these kind of structures where long bridges are there. And then you can see that it's made of curved structure, but then it's individually, it is made up of small linear structural elements like rods or beams, which are in a certain systematic geometric manner, depending upon the design. And they are joined to each other so that it forms the whole structure. So that is a complex structure. And these kind of structures you can also see on the right side of the diagram, and where you see these kind of factory roofs or maybe long theaters and so on, where the structures are made up of small linear elements. So these are called the frame structures because the kind of loading is not only it's complex, but even how the forces are shared by different members is a little complex. And in fact, many of these things, they may act like axial members, they may act like flexural members, sometimes they act like columns, and then sometimes they're also slabs. So that means that the joints are, or even the members, are a little complex to analyze. To move further, so sometimes we also find these kind of simpler structures, which we call as truss structures, where the joints are made by pins. So all the members are joined to each other by the pin connection. And then, as I was saying, so these two type of joining the individual members makes a whole lot of difference. For example, so if you look at these rigid joints, so the joints which are actually, this is actually the practice where they're joined by welding or maybe the rivets or maybe the long bolts where the joints are fixed or rigid. Whereas the earlier one was in the truss type of structure, we have pin joint. Okay, so if you look at a little bit closely at the joints, in the pin type of joints where the members are joined by circular pins, assuming that they're the frictionless kind of joints, then the forces there, maybe you would have done in your structural mechanics, the forces on the pin surface have to be normal in the sense that they're radial, and then all those things put together, they pass through the center, and then all of them can be shown as one single force passing through the center of that. And so if that is the kind of assumption which we make for the truss structures, pin type of joints, then essentially what happens is that each member will be carrying the load only in its own axial direction. It may be tensile in nature or it may be compressive in nature, but the fundamental assumption is that the direction of the force will pass through the pin center. On the other hand, the frame type of joints, which are welded in nature or bolted, They are a lot more complex. And then the members may also take transverse loads, may also take some moments and so on, which is shown in the right side of the diagram. And then it's a little bit more complex than the pin type joints. Okay. So what we do is that we will first take up the pin type of joints, in the sense that we take up planar trusses. Yeah, these kind of planar trusses, which are two-dimensional in nature. And then the forces on the system may be in the XY direction, or a combined X and Y at an angle also. And so finally, the supports are also there. And our interest here is to find out, primarily, to find out the deformation. More than the deformation, we would like to find out what are the forces each member is subjected to, and we would like to find out what are the stresses in each member, so that we can use it for design purpose later and make the structure safe. Okay. So like this, so we have, as I was saying here, so this is a little bit more in detail, so that just to show that if you look at the internal forces here, as I was talking about, so because of the pin joints and because the members are thin and the assumptions which we made, so the internal forces are always axial in nature. So you can see that the complete dotted structure is the whole structure, and then you can also see the arrows which will tell you the internal forces on each member. So the basic important thing here is to realize that under this kind of assumption, so we can assume that each member here is going to carry only the axial type of forces. Okay. So this is the basic introduction for the following analysis. So we can assume that they are members, axial members. So in the axial members, it's also important to realize that if the axial member carrying a force like this one, F, and as we just said that the forces are only axial in nature, and then the relationship between the axial force which is acting on the member and then the deformation here, say by an amount here. So if F is the force, axial force or internal force, and delta is the deformation, we know from simple analysis that relationship between the deformation is by A, E, right? So F is internal force, A is the cross-sectional area, and E is the Young's modulus, right? So this is the thing, and then this is in two dimensions, right? So even in two dimensions, the structure is two dimensions, the axial force and the deformations are related by this simple relationship. So we'll still make our analysis a little bit simpler and more basic by taking a system of these connected bodies or the rods, or even for that matter, we can just change it to a simple spring mass system. What is this here is that this is by A, and also we have to put the length here. So if the length is there, so if we also have to include the length of the truss member. Otherwise, I have assumed to be unity, but it is FL by EAE. So this is the thing. So we can also actually replace it for, if you want to make an equivalent of this one, for this also simple, by a force which is having a linear stiffness of K, and same thing as F here, So here, then here the deformation here again. So we can write it as F by K. And if you compare this K with the stiffness here, the K is the stiffness of the spring. And if you compare these two, the K between these relationship between the spring and the rod is nothing but it is AE by L. So either we can use AE by L and we can use K. Now I think you understand the relationship between these two. Okay, so this is what the element analysis. So this is one element analysis. So as I was telling that this is element analysis. So as I was telling, so that we can very easily identify the basic elements in the structure. So the basic element in the structure is one member, one truss member here, and whose the deformation equations can be written as delta is equal to FL by AE, or you can also, if you write it in one dimensions, then it can even be K is equal to AE by L. So let's just take it a structure now consisting of only springs and you can write any number of springs here. So this is here at this end, this is connected to a rigid support, and at this end you have an external force like this one, and here this is a one-dimensional structure. This is one-dimensional in nature. So that means that from 2D to 1D to a simple truss structure, we are replacing it by the simple spring masses. So we can say that this is having a number of springs, 1, 2, 3, 4, 5. So this system consists of 6 springs, and each one of them may be having its own stiffness, right? And acted upon by a force at this end, or it can even be forces at several places. So for example, you can also apply a force here, right? So this is one thing. So these are the elements which you can identify very easily. So the whole structure is now consisting of either this type, or if it's a 1D, so we have this kind of element. So there's something other term which we would like to introduce is the nodes. So the nodes are, we identify them as the joints where the members are connected to the other elements. So this element has starting here, so maybe here, so let us say here 1, 2, and 3, 4, and 5 here. So we can identify 5 nodes. So in fact 3 is the same as this one because it's one-dimensional in nature. So we have 5 nodes and 6 elements, right? So in this particular example, so we have 6 elements and 5 nodes. Okay, so this is very easy to understand that the elements are individual members which are connected to each other at the nodes, at the nodal points. Okay, so now we want to analyze it for deformations and stresses. So stresses we can get by analyzing the internal forces. All right. So let us see now. This is the basic equation and 1D, and this is the 1D structure which we want to analyze. So now let's go back to this 1D element and then try to put it in a general configuration. So this element equation, now let's go to the element equations. So element equilibrium equations or element governing equations which we want to develop. So the element governing equations is the equilibrium of the spring like this one. Okay, if it is, this is the natural state, and so after applying a load F here, so it has deformed from its natural state here by an amount delta here. So that's what we have already used. So I want to put it in a general reference coordinate formulation. So this F is, as we have seen there, it is delta is equal to F by K, where K is the stiffness of the spring, right? So this is Fy is equal to delta by K. So this is the deformation and this is the internal force. So what we would like to do is that we want to put it in a one-dimensional reference direction, in the sense that if this is X is positive direction of X is like this, so everything measured in the X direction is taken to be positive. For example, here, this is the original state, and here it has moved by okay, all right. So this point 1 here, and this is the point 2. So 1 has gone to 1 prime and 2 has gone to 2 prime. So what we are going to represent is the force. So the force here, now basically the forces are like this at the element level, but we want to represent everything in the F1 here, and then here we want to show the force again in the positive direction. So F1 and F2, we are not showing them in the opposite directions, but we are showing them in the same direction. Together with now the displacement or the deformation here is U1, and here it is U2. So U1 and U2 are the deformations of the node 1 and 2, and small f1 and f2 are the forces acting at node 1 and 2 in the positive direction. So everything is in the positive direction. So now we want to develop the relationship between the forces F1, F2 and U1, U2. So in the positive reference direction. So basically what we know here is, what is that? So if you compare it with the F here, we know that F2 should be, or F1 should be minus F2 and should be equal to F internal forces in comparison to that. And then we also have another relationship here. So F is also equal to K times delta, and which is equal to K times U2 minus U1, right? F is equal to U2 minus U1 times K, right? So now let's put everything in the order. So now if I write one after the other, so F1 is equal to F minus F2. I'm sorry, this is F is equal to K delta. F1 should be equal to minus F2. And here I should write F2 is K times delta. Okay? Right? I'm sorry, there's a small mistake there. And then now let's write it as F1 is equal to minus F2, and F2 is this one, F2 is K delta, F is this, and so we have F1 is equal to K times U1 minus U2, and F2 is K times U2 minus U1. Okay, so this is now everything is put in the basic reference direction. So F1 and F2, we have this like this. So let's put them in the basic reference direction. Okay, so we are now we can write it them as F1 and F2 is equal to, we'll write it in the K minus K and minus K and K here. Okay, so this is the basic relationship between the forces and the nodal displacements. So everything is in the positive direction. F1 and F2 acting on the element in the positive direction, and U1 and A2 are the nodal displacements in the positive direction. Okay, so this is the element equation. Now let's look at the next step is going from element to the system equation. So let's take, instead of these 5 elements and so on, so just for the sake of assembly, so let us consider the system to be only 2 elements and 3 nodes. Okay, so something like this one, just in series. So in this, now this is the system. So we have node 1, node 2, node 3, and this is element 1, this is element 2. And then there can be external forces here, F3 external, and here F2 external superscript, and F1. So essentially what we are trying to get is that a relationship between these external forces and the displacements of these nodes 1, 2 and 3, the U1, U2, U3, right? And now let's look at what we have obtained so far is the elemental equation. So these are the forces acting on the element when the element is written as a free body diagram, right? So now let's look at how do you combine them. So how do you combine them? So let's look at this element. This is element 1. This is element 2, right? And the element 1 here, which has nodes 1 and 2, and this is 2 and 3. And the forces here are like this. So F1 and F2. And here also we have forces like we call it as F2 and F3 here. But let me just F1, F2 is repeated. So F1 coming from element 1, F2 element 1, and this is on 2, and this is on also 2, F3 on 2. So these are the basic forces on the element, right? And then what we would like to do is that, and apart from this, we also have external forces. So how do we combine them? So let's look at this one here. This is the node here 2. And if you look at this part, the forces acting on the node 2. So if you look at node 2 here, and similarly we can also write it for node 1 and 2. So we are taking node 2 because it is connected to two springs. Okay. So if you, these F21 is the force acting on the element 1, and F22 is the force acting on element 2. So, but if you look at the element node 1 here, so what is the force acting on node 1? You can assume that it is a small particle with 0 mass. But if you look at the force acting on node 1, so this is the nodal equilibrium. Okay. So I'm acting node 2 of node 2. So how do we write the force acting on node 2? One is that there is an external force here, right? F2 external force. And what are the other two forces that are coming by the element 1? So by element 1 on this node 2 is F2 of 1 in this manner, because this is the force acting on element 1, while this spring will be exerting an opposite force at the node 2. So the same thing is true here. This is F2 by 2, right? So these are all the forces acting on the node, and all of them put together should be under equilibrium. So all these three forces should be under equilibrium. So if you want to use equilibrium of node 1, so then what do we have? So it is minus F2 of 1, right? And plus F2 external and minus F2 of 2. Right? So this is how the equilibrium of a node, while this was equilibrium of the element. Okay. So what we do now here is write these things. For example, we wrote this equation for any element for that matter, and then it can be applied to element 1, element 2. Now let's look at this one. How do we do it for, how do we make use of this nodal equilibrium to get the system equilibrium equations? So to use this one, so what we have is that we have the data already from equilibrium of element 1 equilibrium. So where we had what? F1 plus F2 of element 1. So we had stiffness of the spring. Now I have to say K1, and so this is for element 1, and this is element 2. Similarly, so we had F2 on element 2 and F3 on element 2. So we have K of 2 minus K of 2 K of 2. All right. So these are elemental equilibrium equations. And now we have derived the nodal equilibrium. So can I do this one? Can I write this in terms of the nodal displacements? So now let's look at this one. For example, this F2. So F2, if you want to get it, F2 of 1, so it is nothing but K of 1, U1, K of 1, U2. So this is this one. And this is the external force. And this is minus of F2 of 2. So that means that it is K2 of U2 minus K2 of U3. And so this is all add up to 0. So that's this equation, right? And can we write this? Can we do this? Combine them so that, so what we were talking about is these are the elemental equilibrium equations, and this is the nodal equilibrium. And what we are trying to do is that we are trying to substitute these forces, the internal forces, into this one. And this is the equation for this one. So what we have here is that if I just K1, U1, and then I'll collect this U2 here, and then it becomes K of 1 plus K of 2 times U2, and then U3 you have plus K2 of U3 plus F2 external. So what we can see here, the one in the bracket here depends upon obviously the material constants, spring constants, and of course the U1, U2, U3, the nodal displacements, whereas this F2 is the external force. So like this, we can write down the equilibrium of node 1, equilibrium of node 2, and so on. So if you write the, so if you similarly, if you, I'll just write it here, please. Similarly for node 1, node 1 is acted upon by only element 1 here, and then what we have here is what we get here is minus K1 U1 from this equation. Okay, this is F1, this minus Q1 minus K1 U2. Let me just see here, minus of this minus of K1 U2 plus F1 external will be this equation. And then similarly we can also write it for node 3 is that for node 3. So we will make use of F3 here. So it is minus K2 times U2 plus K2 times U3 plus F3, and this is with a negative sign here. So if you, these are considering the nodal displacement, so we can combine all of them into one matrix equation like this. It is K1, this is coming from, so this is coming from this equation, So writing down this equation, the first equation is coming from the equilibrium of node 1, and this is K1, it's going to the other side, and then this is K1 U2 and nothing of U3, and then here this second equation is coming from the nodal equilibrium of this one. In fact, there is so here we will have minus Kf1 and K1 plus K2 and minus K2, and multiplying U1, U2, U3. And then the last one is minus K2 of U2 plus K2 times U3 will give you the F3 external here, right? This is the equilibrium equation for the system. So what we have done here is we looked at the equilibrium equation of an element, then having all those independent equations for each of the element, then we looked at the equilibrium of each node, each joint. This is the assembly procedure. So the second step is the assembly procedure is by applying the equilibrium of the node. And using that nodal equilibrium, so we got the equations connecting to the external forces. So this equation, the final equation, is the equation of the whole body. Here we have only two elements, so this can also be extended to any number of elements, right? And remember that these are all very, very simple problems in the sense that we assume that they are all spring elements, they are all in one dimensions, and the forces are all in the x direction, as well as the nodal displacements are measured in the x direction only. Okay, so this is the final set of equation, so which connects the global displacements U1, U2, U3 of the three nodes, and these F1 external, F2 external, F3 external are the forces, external forces which are acting on the system. Okay, so we will take this as our next step, and then we will move on how to apply the boundary conditions. Okay, so apply the boundary conditions in the sense that some of the nodes are constrained, okay, because they are rigidly connected to the support. Continuing our assembly process, so we can also look at the assembly slightly in another angle also. So for example, when we have this two element assembly with the three nodes, so which we said that we can write elemental equations for each individual element like this. For example, number 1 will constitute the stiffness of the element 1 of the spring 1 and together with the forces acting. So on this side we write F1 of 1, F2 of 1 acting at node 1, which depends upon the nodal displacements U1 and U2. So similarly for element 2, so we have F2 and F3 being contributed by the displacements of node 2 and 3. And we also know that here the summation of these two is equal to the total external force here. So that means that the total external force F2 can be considered to be divided into F21 and F22, or the summation of F21 and F22 can be considered to be equivalent to the external force F2 here. So similarly here, this force F11 can be considered to be equal to the external force here. So thus the summation of these two will lead to the external forces here. So we can write the external forces here, F1 and F2 contributing at node 1 and 2, of course. So this we write it coming from element 1, okay, at node 1 and 2. So similarly here, element 2 will be contributing to element node number 2 and 3. So the sum of these two will be equal to the external forces here. So this one can be obtained by this one by adding an extra third row and a third column here. So you can very well see that this is equal to this one, just like this one. So similarly, this one, a contribution from element 2 can be seen coming from U1, U2, U3, and the top row and the first column are zeros because this element will not be contributing anything to node 1. And these two put together, since this column is the same, so we can keep it common here, and these things can be added as it is. The value here, K1, and the 0 here will be adding here. And similarly here, for example, the middle one gets K1 and K2 contribution, and this is what it is, right? So you can see interestingly here, so this part here is nothing but your element 1. So what we are talking about here is that we can see that this first, the 2 by 2, that's the first row and second row, first column and second column, which are coming from element 1 here. And whereas here, these 2, 2, 2, 3, 3, 2, 3, 3 are coming from element 2, and then they are added like this one. So this is another way of looking at our assembly procedure. So that means that element contributions are added to get the system of equations in which these forces which are coming on each element are added together to get equivalent to the externally applied forces. Okay, so this is how we can look the assembly in this manner. I think I'll stop here. So have a good day. So we'll continue in our next class. Bye.